Okay, I think it's time to start. I hope you can see the presentation that will guide this introduction. And of course, let me say that me and all the other organizers, we are very pleased to open this workshop day at ICPM. I think workshops are really interesting opportunity because in general, the papers that are presented there have a lower maturity level, but has great portion of original and innovative ideas. And also, if you look to the program that we have today, you see very interesting topic of discussion. So I think you will enjoy this section. From the program, you probably noticed that the ML4PM and the PQMI workshops joined for an invited keynote opening today. So we are now briefly introducing the two workshops before launching the activities, so the keynote and the sessions. Be aware that some sessions are in parallel. So people interested in the PQMI session will be required to move to another Zoom meeting using a different link that was published on the website of the conference. So I have a couple of recommendations about the policy to be followed during the video conference. So we ask you to keep your camera on to let the others see the presence of the audience, but also please be sure that your mic is muted until you are not called for the discussion or for presenting something, of course. So please have a check to your mic and mute your mic if you are not speaking. People are joining. In any case, let me start with a short presentation of the ML4PM workshop. So this is the program of the first international workshop for leveraging machine learning in process mining. So you know we have this initial session with a keynote presentation provided by Professor Damiani. Then we have two sessions, one starting at 13:30 and another one starting at 14:45. Let me, of course, express my thanks to the organizers. With me, we have Professor Silvio Barbon from the University of Londina in Brazil, and Professor Annalisa Apice from the University of Bari in Italy. And clearly, the program committee that made possible the review and the assessment work that was done during the process. We have now a short introduction about the topics that will be discussed in the project. So I would like to give the floor to Professor Silvio Barbon to provide us with this short introduction. Thank you.
Okay, now I have to do the stages. Now I have to look at what is the message you sent to me.
Hi everyone, my name is Silvio Barbon Jr. I am a professor at State University of Londrina, Brazil. It's a pleasure to contribute to the ML4PM workshop in ICPM 2020 with Professor Paulo Ceravolo and Professor Annalisa Apice. Also, I would like to thank our program committee and the ICPM organization. So now I would like to present some directions and the current achievements delivered by the accepted papers. We received a total of 15 high-quality submissions, and with 7 were accepted. The accepted papers are contributions from 6 different countries, 3 for Germany, 2 from Italy, and 1 from France, Spain, Egypt, and Norway. Some of them were collaborations between different countries. Our target was to select papers that match high-quality machine learning proposals towards advanced and process mining tasks. Regarding the contributions on PM tasks, we received 5 papers devoted to conformity checking and 2 for process discovery. The proposed goals were successful completion based on clustering, feature extraction, reinforcement learning, and recurrent neural networks. This last, the neural networks, was the more than half of the papers. The most popular technique was long short-term memory, deep learning algorithm ideal for time series and temporal information domain. It is important to mention the more popular application in the PM spectra was predictive process monitoring. Part of the papers shared some open issues and paved the way for future research. So the first open issue was the usage of time information between cases, events, focus on delivering a reliable descriptions of the process. In other words, time perspective can bring more insights and contribute to a reliable machine learning model for PM monitoring tasks. I would like to mention that this monitoring tasks was the most popular application in our workshop. Another issue is the demand for prior knowledge when dealing with real life scenarios. This concern puts some light in the distance between the synthetic event logs and the real ones. The gap between the synthetic and the real event logs pose some challenge for real life applications of PM. So the final important aspect related to these perspectives, I mean, an additional information resource such as cost, user, and unstructured data can bring important insights when monitoring the process. So in our workshop, we observed that these additional perspectives require, for example, the usage of text mining and encoding algorithms can bring future research proposals and improve the current models. So this is, summing up, this is the most important things or the main achievements that we can got from our papers or accepted papers. And I expect that all presentations can deliver a good time and exchange of knowledge. So thank you for the opportunity to share this insights, and have a good workshop. Thank you.
Thank you, Silvio, for this nice introduction. And now the floor is to Artempoli Pani, that will present the PQMI workshop. Thank you, Artem. Now you have to unmute.
Hello, can you hear me?
Okay, now it's working. Hi, Ernesto.
Hello, how are you? Thank you. I hope you can hear me. Sorry for, but I was unmuted before, so it was disturbing the previous. So now I am muted. I took a moment to unmute myself. So first of all, I would like to thank you very much for inviting me.
Ernesto, excuse me, but we are still a few words for the introduction.
Sorry. Okay. In that case, go ahead, and I will unmute me later on.
Thank you so much.
Yeah, so I will just say a few words quickly. So this year we had 6 submissions. 1 paper was also transferred to us from another workshop. So we reviewed 7 papers in total and accepted 3 papers. The program is on this slide. We'll proceed with the keynote just in a few minutes. And we have 3 very nice papers. Presentation will start at 1:30 p.m. So 1 on conformance checking, so approximating alignments, which is a very interesting topic, very important topic in process mining. We will also have a paper on stochastic process discovery. So the topic of stochastic process mining now slowly emerges, and hopefully there'll be more attention to this topic in the years to come. And also the paper on using graph databases for process mining. So this will be 3 papers. Those who are interested, please join us. Next slide, please.
Yes.
Yeah, and just on behalf of all the organizers, would like to thank to all the PC members for great work and timely reviews, high quality reviews. Thank you for being with us. That's it. Let's move to the speaker.
Thank you so much. So we go to the keynote speech that will be proposed by Professor Ernesto Damiani. The title you see is Applying Artificial Intelligence to Business Process Management, Opportunities and Pitfalls. So we know that process mining is a remarkable tool for studying the control flow of a process. So you can identify patterns like the lead time, waiting time, loops, bottlenecks, etc. However, the core process mining algorithms are not enough for addressing all the tasks that are related to process enactment, especially. So in general, when you are focusing on the optimization or on predictions. So on due respect, machine learning can provide a powerful complement to process mining. So, of course, this view is not new, but it's very topical because machine learning is a field attracting a lot of attention, investments, and efforts. It is then evolving fast, offering new solutions and touching so many problems and so many contexts. So continuously refining its techniques. More recently, scholars started to apply machine learning not just to predictive analytics, but for supporting other stages of process mining, such as tracing coding, enrichment, feature selection. But Silvio gave us a good overview, I think. However, if we want to wisely adopt machine learning, we need to understand its nature, because its nature is symbolic. It means that it is not monotonic. We cannot transfer our conclusion from one case to another. And this will be the central point in the speech provided by Professor Damiani. I'll spend just a few words for introducing Professor Damiani and not go for an enumeration of the titles he collected along his bright career. But looking to his record, I'd say you can see the impressive volume of the collaborations he developed and the wide set of topics he addressed. In most of these topics, he was able to provide contributions with significant impact. But as said, we cannot follow his CV, it is too long. Let me just say something about his recent activities. He is now Senior Director of the Artificial Intelligence and Intelligence System Institute at the Khalifa University in EU AIE. He's leader of the big data area at the Etisalat British Telecom Innovation Center and full professor at University of Milan, where he leads the Cesar Lab. So I think you can understand that thanks to his position, in last year he had the opportunity to lead or supervise a great variety of projects in the area of cyber physical system, artificial intelligence and intelligence system, big data analytics, and machine learning. So he is in the position of having a very up-to-date overview on how machine learning and artificial intelligence are changing organizations. And by organization, I mean this in a wide sense, not the dynamics of an organization, the design process in organization, especially the technology design process, and of course also the business process management with the documentation and the decision-making procedure it requires. So now, Ernesto, the stage is for you. Thank you so much for provide your availability for this talk, and let's go ahead. Thank you.
I hope you can hear me. So
Yes.
I will try to share my screen. I need you to stop sharing your own screen though.
Exactly. Also, I have to give you the
presenter's rights.
Yeah. You know what? I'm not allowed to do it, but I will ask to the technician. He can do it. So I can stop sharing.
Okay. Let me see if I can share my own screen. Yeah, it looks like I can.
Good.
So just 1 second.
Yeah, you're also co-host as well.
Yeah. So let me see.
Okay, in the meanwhile, let me recall everybody, please, to unmute your microphone to don't disturb the presenter.
Okay, here we are. Okay, so first of all, once again, thank you for the kind introduction. It's, I mean, when someone starts saying that your CV is too long, it normally means that you are old. So this is, I sort of, well, let's say I take this from the at face value. I hope it is just the density of the experience and not the length that is brought to the to that comment. Anyway, I will basically have a lot of slides in this presentation. My idea was to try to discuss and present some of the opportunities and also highlight some of the pitfalls that basically this trend towards the wide adoption of machine learning within the business process analytics area is bringing about. And I've seen that in this workshop, I mean, this is the topic of the workshop, so a lot of people are experts, but in applications of machine learning to business process analytics. So I hope that it can stimulate also a discussion. Maybe you have different views, maybe there is something I forgot. So without further, I would like just to start. I have an initial set of slides that were meant to make this presentation self-contained. I don't want to bore you with what you know better than I do. Basically, we are talking here not of a general, the general application of machine learning to everything. We are talking specifically of an area, the area of business process analytics and business process mining. And in this area, we have, of course, the people who do models and they explain how the processes should be. And then they have the people who do the collection of observables and they do the logs collection and the logs analytics, and they basically analyze the processes as they are. And of course, we have the point of contacts, which are the detection of violations or the detection of compliance and conformance, where you basically try to compare what happens to what you thought could happen or should happen. So I will, the basic data observables that we are interested in this area, but also in some other adjoining areas, are basically the activity logs. I mean, the logs that tell us what happened, what are the events. And you can see here one example in which I have a few activity carried out via a client of an application, and they have their timestamp, and they have some context information like the IP that the IP address that was used in order to carry out that activity. This is the clerical process type of logs. In the clerical processes, which are the processes that are done by white collars, in a sense by using programs, software applications, we get basically a nice property of the logs that are, their granularity is the same as the process models. We have the activities listed in the logs are exactly the same activities that we use in modeling the process. In this case, for example, field complaint, reject, review, all those activities are probably at the same semantic level of the activities that are listed in the business process model. This log is an instance of. So this log is a case of a business process model, but they have the same level of granularity. So, okay, let me just now remind you that this type of property of it being at the same level of semantics makes it, I don't want to say easier, but it is a basic assumption that made it easier for a long time to come up with the tools and the algorithms for checking conformance and compliance. If there is a sequence in the log that is not allowed by the model, I will basically flag it. And of course, it may be very difficult. There is all the huge amount of literature that you know, but the problem is quite clear. I mean, it's like having a series, a sequence of letters, and then having some sort of a set of rules that tells me which letter is allowed to come after another. And I will basically be able to verify by looking at the log whether a violation occurred, using the log as a grammar, in a sense, that tells me which strings I can expect, using the model as a grammar, to tell me which strings I could expect to find in the log. Now, for a long while, we went on by, including myself, but all the community continued to propose advanced techniques based on whatever, language theory, infinite states automata, you name it. A number of techniques have been used in order to handle this problem of checking the logs with respect to some model. Now, we have a lot of interest in using machine learning, and the machine learning trend is global. We are applying machine learning in all the areas. But what are the reasons why people want or are interested in using machine learning, apart from the fact that it's fashionable? Well, first of all, we would like to have these checks to have a predictive component. We don't want just to notice the violation after the fact. You want to be able to predict the violation. And so timely prediction is also very important. So there is a strong push in that direction. Well, machine learning is not the only technique that is available to build a predictive system. It's not the only one, but it's a usually successful one. So this one was one of the first reasons why people started to be interested in using the machine learning for log analysis. And the second is that the other techniques have a lot of course, disadvantages, and we want to explore whether with machine learning we can come up with something which is effective and avoids any manual intervention. So the common objective of this machine learning application is basically coming up with an end-to-end framework that can allow us to sort of looking at the logs and coming up with a prediction or a classification or an anomaly detection that have to do basically with the business process model. If I don't have a business process model, I may have some simpler normative definition that I can use. Now, the problem is that the opportunity is great, but there is a first level of a first problem that sort of emerges. The problem is that the machine learning, the data that are collected and that the machine learning model should look at, normally do not have the property of being at the same semantic level as the business process model. We have data collection layers that collect the data about events, which are much simpler and are in whose relation to the activities of the business process model is well, not always clear. So you can find many variations of sequences of events that happen in the log, and they all correspond to the same high-level activity that is mentioned in the process model. Now, the machine learning is deep learning. Now, you could say, well, this is a problem that existed before. Yeah, but the deep learning notion makes me think that maybe I will be able to bridge the semantic gap between the low-level events that are sort of collected through the sensors to the conclusion, the inference that I want to make, which can be, as we were saying, a prediction inference, a classification inference, or an anomaly detection inference with respect to the model. So can I use machine learning also? The opportunity, at least, that comes to mind is that to use the machine learning also as a way to bridge this semantic gap. Is by no means the only way that in which you can bridge this semantic gap. But since the deep learning has shown its capability in bridging this gap in a number of application areas, we are asking ourselves, can we, or at least the opportunities is seen by many, that it can also bridge the semantic gap in the log analysis. Can I just look at what happens using the sensors that I have and then come up with an inference that is about maybe a prediction of compliance with the business process model that is actually mentioning activities which are at an entirely different and probably more abstract semantic level than the basic events that the sensors are collecting. Can I use, and that it looks like another opportunity for using machine learning, bridging the semantic gap in a single step. So I would like to offer you this vision of a framework in which we have event logs at a very low level, and we would like to bridge the gap and do inferences that have to do, so we would like to have a model that makes an inference, for example, predicting an upcoming violation to a process model. And as an input, it has the context which is given by the model, but it has logs that semantically are very far from the activities that the model mentions and that the model prescribes. So we would like to see if we can use machine learning. It looks like an opportunity, right? So we'll try to go into a little bit more detail now. So first of all, but before going into the detail, I want also to say that there is also a meta model that I needed to show, which is the fact that whenever we try to apply the machine learning approach to a scenario like the one that I tried to describe quickly, we also need to take into account the fact that the application of machine learning is itself a process. It is a process that improperly has been called, for some reason in the literature in the machine learning field, some people call it a life cycle. It's not actually a life cycle to me, it's just a process model in which basically applying the machine learning to any scenario follows a certain let's say, basic template of steps and activities itself. So this I want to show because whatever I will talk about is in these two boxes here. Of course, there are other problems. To bridge the semantic gaps, we also need to have an ingestion, the capability of collecting observables from the sensors, from the low granularity, the fine granularity event. Well, we must have it. We must find a way to solve all the problems of data acquisition that with respect to the clerical business process in which we have a very comfortable logging done by the application itself maybe. So what I call the SAP style of logging in which, well, if we want to log activities that are cyber physical, that involve events that are very small, very fine granularity, of course, we also need to do these boxes here. But what I'm going to speak about today is focusing on these two boxes, training and tuning. And we will come to that soon. But I wanted to show this just to clarify that if we want to use machine learning for inferences about business process models and business process logs, we also need to think again to the platform for data acquisition and to the platform for basically using the results. Anyway, so the first question that I have is open to discussion is, well, shall we do it in one step using machine learning? So shall we try to let the machine learning support learn any association between low-level events and a semantic aggregation that can be called activities, meaningful activities or whatever? Or should we do it into steps and use machine learning to establish a symbolic mapping between the low-level events and the activities? So you see, this is a choice. And in both cases, machine learning will be useful, but in the case of the second case that I'm mentioning, the machine learning will be helpful in establishing an aggregation of possible patterns of events in the low-level events that will be mappable to semantically meaningful activities in the business process. This way is preferable for explainability. It has these advantages, though. It is preferable for explainability because if you see here, if I am prescribing to some employee to wash hands, and then all I have are sensors in the washroom, and the sensor in the washroom can only tell me what the employee is doing, whether he's pushing the button, whether he's opening the water faucet, putting his hands under it, maybe if there is a sensor there. But of course, they are not telling me whether the guy is actually washing the hands or not. So the explicitly mapping the low-level events to the higher-level events is basically something that can help in justifying the inference that I later will make about, for example, compliance or non-compliance. On the other hand, if I try to do this mapping, I may end up with a system which, from the accuracy point of view, is less performant than a system which will bridge the semantic gap in a single step. Okay? If you want to go 2 steps, meaning that you want to do the going from the events that you can read from the environment to the semantically meaningful activities in 2 steps, you need to solve 2 problems. The first problem is the problem very well known in the community, or log segmentation. I have to understand when to stop looking. Of course, in the clerical processes, Paolo and myself, we wrote a paper years ago in which it was very easy because we could use the time stamping. So whenever I had the high density of low-level actions in a certain interval of time, I sort of grouped them together. And when I had a longer interval, I sort of took that as a sort of a, separator between one activity and the other. But in many cases in the environment, the time is not helpful at all. So the log segmentation problem is not easy at all when you have especially a time distribution of the low-level events, which does not help you in doing easy separation of the event sequences. And secondly, we have the lifting. Once I separated the log into blocks that will actually correspond maybe to some semantically higher level activity, how can I match how can I decide which activity should be mapped to that log? So, well, I don't want to bore you. These are problems that are very well known. How can you use, what I'm looking here is the opportunity of using machine learning to do so. I'm not talking now of the opportunity to use machine learning to bridge entirely this gap and to feed the deep learner with the low-level event sequence as it is, and to come up with a direct inference about the process. The reason why I'm not talking of that alternative is that I would like to maintain that it's very, very hard to make it work. At the moment, I haven't seen yet a single step bridging successful in a complex process. But you may know of someone or somebody that did it, and in that case, it will be an interesting topic for discussion. So let's assume that the opportunity we are looking at is using machine learning to do the double dip, meaning to do first segmentation and then from the segmentation go and do the mapping to some semantically richer representation of activities. Well, I don't have to, you know what is in this slide. It's not an easy problem unless you get the timing on your side. So many techniques that are used, machine learning techniques that are used today are basically related to the machine learning techniques that are used for an LP. So in the machine learning techniques that are used for natural language processing, many of those start by considering the text in a different way, looking at the text in a way that can be later recognized sub-symbolically. And the same thing we do with the logs. What we do, for example, we can do a sort of an n-gram encoding in such a way that we have n-gram of variables of variable length that encode my log. And this way I'm sort of going, you see, from a representation which is a timed to an histogram-based representation, in which what I have is basically the occurrence, the frequency of occurrence of the occurrences of the different n-grams that I can find in my log. Each, of course, letter here is an event of a low-level sensor. It's not an activity of the process model. So this type of transformation allows me to use machine learning techniques that can come up with the right separation among the events. Here I'm showing basically maximum likelihood type of approach that lends itself to be implemented via machine learning model. And basically, the maximum likelihood of approach is trying to find the, given the frequencies of the n-grams, it is trying to find the separation that maximizes the likelihood of the entire log with the separators in. So this is a way that in which a problem about what is the sequence of activity, the human would use a very different approach, like the human expert. He would basically recognize end or beginning or ends of a sensor data, for example, like open the faucet of the water or press the soap button that I used before, the example I used before. The human would probably look at those anchors in the event sequence, pre-applying some sort of a mapping with a semantic representation. But this type of methods, what they actually do is to bring back the problem to, let's say, a frequency representation. So according to the frequency of the n-grams, I have there, I can compute the likelihood of the log. I compute it with certain different candidate separators in, and I take the separator position which maximizes the likelihood. So this is something that is a lot in our papers, but also in a number of papers from people. Maybe there is one or two also in your workshop. These techniques basically are sort of I call them a sort of a Markovian approach, in which you try all this, randomly try all this separation. Of course, you may also have some intelligence in trying the separator positions, and you choose the separator position that will maximize the likelihood. Okay, so you scan the flow, insert the separator, and then basically based on that, in this case, I'm inserting a separator between the D and the E in this slide, and I have all these candidates, and with this candidate separator in my low-level log, I will compute the likelihood and put it aside, and then I will have another candidate. So this technique easily can be implemented through a machine learning model, and it basically gives you a first approximation of the chunks of low-level events that you should consider for possible mapping to semantics. Then you do the mapping to semantics, and in order to do the mapping to semantics, the problem is to be able to, well, collect the examples. Of course, if I had a human who, looking at these chunks, would put the labels, and then I could easily train a second level machine learning system to be composed with the segmentation one that would generate now a lifted log where the name of the activities would be the name of the labels that the human has added to the different chunks, are given to the different chunks. Unfortunately, there is very little in terms of literature. There is one guy in Japan who recorded for 3 weeks his life in a house full of sensors, and then he manually labeled those sequences, like in having breakfast or brushing my teeth or whatever. But there is very little in terms of and it's not very credible that you will ever have manual labeling on a large scale for this type of association of low-level events to high-level activity. So how the questions for this second sub-step of the double dip mapping from the low-level events to the semantic rich ones, to the activities that are mentioned in process models, is who does the labeling, when, and how. When is important. It's also, I will come back to the when, because this labeling may be obsolete, with an obsolescence, become obsolete at a very different time than the process model. So you have a situation in which you may end up with a system which has different time bombs inside it in terms of, becoming obsolete. And then, of course, the how is also important. We don't have large scale. So, okay, so a lot of people try to do machine learning even in this step. So we had a machine learner model that used to segment. Now we segmented. Now we have a machine learning model that is used to learn the mapping. But before learning the mapping, you want a third machine learning model that learns the training set to be used for training the mapper to the semantic activities. And so basically what you normally do is to use unsupervised machine learning in that case. And I'm just presenting here an example in which you use clustering. But of course, clustering is only one of the techniques that you could try to use. There are many papers in which I am familiar with the pitfalls and the advantages of trying to use and to find the right approach to use clustering. This is what we do in our projects. But of course, I know that other approaches can be used. The clustering is not that easy as it seems, because normally when you do clustering, you get a number of clusters that has nothing to do with the number of activities in the process vocabulary. Also, the clusters that you get may have, some of them, a high number of elements, and some others have a small number of elements. So you may end up with something that is very difficult to use as an automatic labeling device. So what do you do normally? Normally, you do a careful choice of the clustering algorithm. You want a clustering algorithm which is robust with respect to outliers. You want a clustering algorithm that is not easily impressed into creating a new cluster, because you want to keep the vocabulary of the cluster names or the cluster labels small enough to be mappable to the process vocabulary, meaning to the list of the names of the activities in the process models that you want to map to using another model later. And especially you want to do an additional refinement step after you build the clusters. So when whatever clustering algorithm you are using, don't expect high quality in the automatic association to each element to its cluster name as a potential labeling. Don't expect high quality, but it's a starting point. And there are many refinement algorithms that are used successfully. This, you see the second best Bayes selection. We use the silhouettes. We used many of those, let's say, second level choice, because you don't want all the clusters. You want a part of the clusters, the part which maximizes the likelihood, again. So there are also maximum likelihood techniques. Here we use the second best Bayes selection technique in order to extract from each cluster the strong part, the part from which you think that belonging to the cluster may have semantical relevance later. So this is what we normally do. And once we have that, there is the identification of the cluster labels that the human does. The human comes and identifies the cluster name with the process vocabulary. But this is an activity, according to me, you may have a different opinion, of course, that is credible for a human to perform, because it is a mapping of hundreds to hundreds, hundreds of clusters to hundreds of words, meaning activity names in the business process model, not of thousands to thousands or tens of thousands to tens of thousands. So we have the human coming in to find, for at least some of the clusters, a mapping to the activity name in the business process model. Okay, now, so you see, this is the opportunity. We have another moment now. Suppose that we have now to create the network that actually will basically do the, once we have lifted the log, we want the network that will do the prediction and will do the classification or anomaly detection on the lifted log that we have achieved, that we have computed using the the double deep system that we saw in the previous slides. Now, whatever, even after lifting, the big problem is that we are not in a typical machine learning situation. We are closer, you know, to natural language processing again than to image processing. Why? At least this is my personal opinion in application of machine learning to the logs. The reason is that we must have memory. I mean, the right inference about an activity with respect to any business process model, how close is the next violation, for example, or is this activity part of this part of the other part of the process model? Well, of course, they can be answered only if I know a little bit, I have a little bit of memory of the previous activities that are in the process model. So we are in a situation which is closer to NLP because we need stateful machine learning. This is just again, my 2 cents, and we can discuss them. It's a workshop after all. But we need, why do we need stateful machine learning? Because we need to be able to put each of the lifted activities that we get from the sensors in the context of what was done before. And so very little can be done in terms of looking at the single activity. Even if you would do the single dip, meaning that you would try to map directly the chunks of low-level events to some inference about semantically richer process model, I don't think that you could do anything sensible just by looking at the current activity or the current chunk, in that case, the current chunk of the event logs. You need to put things in some context. And I'm sure that you agree, because I saw that in this workshop, most of the papers that use machine learning are actually using stateful machine learning already. So I was quite confident in putting forward this opinion. Stateful machine learning. So what is stateful machine learning, and why are we going in the direction of using this set of techniques for the inference about the logs, the lifted ones, the ones where we already did the transition from the events of the sensors to the activities that the humans consider semantically. Well, this is just the ABC of your classic deep learner. Well, it's not very deep. It's just a few. In a deep learner, you have hundreds of those stages. The problem, again, with the deep learner is that for our application is that we would have to map directly here the event from the sensors, and here to have an inference which is about a process model. Of course, you can also put the process model as metadata as part of the input to the deep learner. But the learning operation here is, how can I say, very complex, because especially if there is high variance in how the humans or the actuators can accomplish a certain activity. If there is a high variability of the sensor events that will be generated to obtain a certain effect, the problem is that the deep learner has to see a very, very high, a very, very large, a very highly dimensional set of examples in order to have seen even, how can I say, a reasonable portion of the different ways by which a certain object, a certain activity can be carried out. So the training of the stateless model is a problem. The stateful model, well, of course, the stateful model knows not only what is basically presented to it, but also it knows what was presented before. And it doesn't have an explicit memory. The memory is obtained, as you see in this slide, normally via unrolling, meaning that the same effect that you have in having memory, so you see this element is not only influenced by this input, but also by the output that was, of course, the output for the previous input. And so in a sense, this is as a memory, because this age value will be computed based on this X, but also on the output generated by the previous X. You can obtain the same result by unrolling, so by redundancy of the elements in the network. So a lot of papers, including the ones in this workshop I saw, use models that actually keep a certain amount of memory in their inside the machine learning model, and they do that via unrolling, typically in the structure of the model, the memory components to become, you know, a sort of delayed input sequence. And the delayed input sequence, here you see the delayed input sequence of an LSTM, which is the model which is people are using a lot today in our inference about logs, about lifted logs, I'm talking always. This model uses unrolling to be able, when I feed it with a certain activity, to take into account also the activities that I fed it before. It doesn't have an explicit memory, but the output for that activity is also dependent of the carryover of the output of the previous inputs that I gave to the network. So depending on how large the topology of the network, how wide the topology of the network is, the higher the memory that it has in taking into account the context of the previous thing. So we are working on stateful, but representation. But we have, this is another pitfall that may be hidden under this opportunity of using stateful machine learning as the way. One typical, there is a very nice textbook that shows this as an example. A very typical demonstration of this pitfall can be obtained if you try to train one of these networks with memory, just to basically solve a problem without giving enough context. So this is the typical case, a case in which I'm trying to learn the consecutive letters of the alphabet. So I have two labels, consecutive, non-consecutive. AB is consecutive, of course, AC is non-consecutive. So let me give to this network, to this LSTM network, a bunch of examples like this. In no particular order, and then later I will feed the network with two letters, and I want the network to recognize whether they are consecutive or not in the alphabet. So this is a typical example that it is in a lot of textbooks, and shows you that the network will perform very poorly. Why? Will perform very poorly, especially if I am basically treating each example, computing the error for each of the individual examples, because normally the state of the network is reset after each batch in the training. So this means that I'm thinking this type of prediction is not really taking into account the context. So we are treating the LSTM network as a multi-layer perceptron. And this example is a very illuminating one in a few master textbooks. So I'm not saying you anything you don't know, of course. But so what do? We trained an LSTM. I will show you the trained LSTM performance in a minute in a number of practical projects. And what we do basically is this stupid trick. We do a single batch training. In a single batch training, you try to have large batches, which normally you don't do in machine learning, in deep learning, because normally you want to have, you see, in order to be sure that you're not choosing a local minimum in the network, in the training network, what you do is you try to sort of have small batches, micro batches that are used in the training of the network, meaning that you compute the error after just a few of examples during the training, and you apply the error to the network to change in the network as frequently as possible. This is what you do in deep learning. But if you do it in the type of deep learning that we want to do, which is a deep learning that takes into account, lets the stateful system use its memory, which we cannot afford having that type of small batch training. We need to do large batch training, which in the end is a pitfall, because it will be easier or more difficult to find a meaningful minimum of the error function for our inference about the log. So this is one of the problem. So okay, let me show you how we did that very quickly, because we are close to the I believe to the end of the talk. We use a bidirectional LSDM with an attention mechanism. I don't have the time to enter into the technicalities here, but many, I'm sure of you already know that the problem also depends on the fact that for different parts of the same business process model, I may need different memories because some of the parts, the inference is more context dependent. In other parts, the inference is less context dependent. So it means that the amount of memory that the network should consider and should in learning does not depend also on the input. So for doing this, there are attention mechanisms that isolate parts of the network topology in order to have a different width of the rollout that I explained before, according to certain type of inputs. So I have this capability of modulating the amount of memory that I am using to make an inference about my log. I'm talking the lifted log always, depending on the specific activity or inference that I'm making, the specific content of that part of the log. So we used this. The ground truth for this is a BPM paper of last year. We used the ground truth. We used, of course, a performance checker that uses basically after the fact violation deduction. So it generates a ground truth for us to predict. And then we do the prediction. And this is the bilateral model where you can find some of the suggestions that I mentioned in the structure here. So the attention layer is trying to modulate the width of the network depending on the particular inputs. For some inputs, I'm looking back. For other inputs, I'm looking back, but with a more limited amount of memory. And the LSTM is trained using big batches, even if it is sort of counterproductive in terms of the length or the duration of the training. Still, okay, we did the testing on some classic data sets from the literature. So this is the CCC 19. I'm sure that, I mean, this is stuff that you know about medical processes. What we found out is that first of all, the segmentation was very effective. You see, we have a 99.35% accuracy. Log lifting also was in the double deep approach was also very successful. But the BLSTM is, I'm going quick. This is a nice comparison that was done by Gagliatello, which is a PhD student of mine back to Khalifa, to look at whether the attention mechanism is actually helping, whether it is useful to modulate the memory about the log, looking at the specific section of the log I'm considering, and as you see, it is. And basically, the total prediction of the location was 99.74% with the 8 events in prefix. I don't want to enter into the technicality here, but we are basically getting very close. But the problem is that it may be log dependent. This is still the pitfalls that I mentioned are not solved simply because one approach worked for one project. We still the understanding. I would like to finish with the 2 slides that Paolo gave to me. The models need to be retrained. This is called model tuning. The problem is that if I created the composition of different machine learning models that I explained in this talk, this composition, the models will age with a different obsolescence rate. And for example, the high-level drift of the names of the activities with respect to in the lifted log will be a different drift than the drift in how the things are made. For example, in the medical field, it's normal that people do things in different ways according to their experience. So the mapping between the low-level events and the activities, that one also ages, but ages very fast because people learn. And so the sequence of low-level events mapped to high-level activity is changing very rapidly. But also you have a drifting at the higher level in which you are the concept of the high-level semantically rich activity names are drifting because maybe the process, the normative, the way things are called within the company is changing. So we need, so this is a slide that is work by Paolo mostly, but shows basically, and by Silvio as well, so by the organizers of this workshop. So I'm trying to, well, basically here you see that there is a lot of a need of retuning. And when you need to do the retuning, which is basically relearning the model, depending on the drift of the concepts, of the high-level concepts, we still don't have a clear, I'm saying it because I am convinced of it, but we still don't have a clear experimental confirmation that the rates of drift in the mapping between the events and the activities is different than the rate of drift in the concept definition at the level of the business process. Okay, so here we have a lot of this, but basically machine learning people, they like fixed retraining windows. They like to retrain all the components of a complex machine learning aggregation all every week, every 3 months, so we still don't know whether a fixed relearning window would be okay for a machine learning based framework for business process log analysis. Okay, I finished. Sorry for this long, but I wanted to cover all the steps. So successful application needs to solve 3 problems, and there is a 4th one that I added. The 3 ones that the literature is already working on, and what I offered is my own point of view in the practical projects that we are following. Double deep or single deep, we do double deep. How to do it effectively? Machine learning will assist in the double deep in segmentation separately from log listing. We need to manage the state in predictive models. This is our job. It's not the job of the machine learning people, because they don't know how context dependent application by application will be, the model will need to be. And thirdly, we need a guide to retrain when it is the case. If we don't retrain or we retrain regularly all the models without looking at the different rate of obsolescence that these models can have, we may have models that will sort of age fast and whose accuracy in the real world. I finish by saying that unfortunately, you know, a lot of papers claim 99.9% like I did. In many cases, in reality, we are facing quick obsolescence and very, very low accuracy just after 3 months of operation. And this is the moment in which the customer kicks you out, because you went promising a lot, it works at the beginning and it doesn't work at the end. Okay, so thank you very much for having me tonight, this evening, and I hope that I didn't bore you too much with this presentation.
Thank you, Ernesto, so much. To clap hands in virtual meetings is not very effective, but please accept our appreciation. Now I think it's time for questions. Please use the chat in order to book your slot, so we can have a organization in passing the floor. Any question? Okay, I will break the ice by asking if you can please elaborate a little bit more on this last point that I think is very interesting. So based on your experience, you say that when you are developing a model, this model is aging very fast. So the question is, do you think that the organization has this understanding, or is still something that belongs to the knowledge of experts?
Well, in some organizations, they know. For example, we are talking medical practice. In medical practice, it is very clear, because they know perfectly well that, for example, a lab technician that goes and does a test, it will use a very different set of low-level actions than at the beginning of once he just joined a department. Even if this person has a long experience in other processes, the people use their hands differently, generate different sensor events. A long time, that is the part that ages very fast, for example, in medical applications. For the COVID, we had that. I was part of the COVID task force in the UAE. We have this notion that the actual sequence of actions, low level, which were sensor, of course, were so readable with sensors, that were done by the same operator at the beginning of a period or after 3 months were very, very different, because the guy would learn how to, for example, how to start an equipment in a faster way, will parallelize certain things that he saw at the beginning. You have a typically very a serial behavior. So this type of changes in the behavior are changes that will reflect in what is the chunk of low-level events that will be mapped to high-level activity. That ages first, at least in my experience. Ages very fast because it is linked to the human in many cases, not always. It's linked to the human learning process, which happens in parallel. You know, people, even the same person, will behave differently for doing the same activity after a certain period. So this ages fast, and this is known within organizations. This is known because they know that people. But the fact that if you go to an automatic, for example, an automatic predictor of violations in terms of high-level events, the fact that that predictor will also age when the OMS documents change. And this is Silvio and Paolo are experts in this, because the names of the activities will be no longer, the business process vocabulary is drifting, and the definition of the activities are drifting. So we have a very different rate of change. And the organizations know, maybe if you talk to them, they know. But then in reality, these different time constants between the changing of the underlying knowledge that will trigger retraining for machine learning are not always, for the moment, there is no awareness that they must be sort of adapted, or they must take into account this difference. So they are aware at the level of discussions like today. In practice, the reflection of this awareness in the practical systems is at the moment limited, in my opinion.
We have a question from Annalisa Apice. I give you the floor.
You're still muted.
No, she's unmuted. Annalisa, you can speak. Can you hear us? I don't know. For some reason, you are unmuted here in the system, but okay, maybe
I cannot hear them.
Try to speak. No, I'm sorry, I don't know. Strange.
I think she's typing.
Yeah. Okay. In the meanwhile, we have another question from Praveen. Praveen, I can give you the floor. Okay.
Hello, can you hear me?
Yes.
Yeah, so I wanted to know these low-level events which you described in the first slides. So I thought of these low-level events as like some processes inside bigger processes. Is it so?
Yeah, in a sense, it is so. Normally, they are the sequence, or there is a relation between the events that are the sensors can gather and small, let's say, finer-grained activities that are carried out. But this relation is can basically can have different statistical properties, meaning that you may have different variants of the events that are actually correspond to a single activity. So you may or may not easily find a parametric representation of these low-level sequences that will correspond to a single activity. Remember, if you think of the business process representation like a grammar, well, we do it at the second level when we have the activities and we have the business process model. Sometimes we could consider the business process model as a sort of a accepting automaton, right? Or sort of a high-level representation. For the lower level representation, yes, you have sequences of fine-grained events that all correspond to a single activity. But the relation is not exactly the one that you can consider the activity as a sub-process, because sometimes the sensor event does not correspond to a sub-activity. It corresponds, for example, to a context condition. You may have, for example, a sensor that tells you whether the light in the room is on or off. This is not an activity of the human. So, of course, you could imagine to map the low-level events to the activities using a sub-process model type of approach, in which each high-level activity is itself a process that has inside the sensor events. But the sensor events, not all of them will tell you about a sub-activity. So, I mean, this is not what we have done. In principle, you could do that, but I think that in that case, for example, in some manufacturing setting, you could probably do that, because in that case, the sensors would be there to be mapped to elementary subcomponents of the activity. But this is not always the case.
Okay, thank you so much. I'm sorry, we have now to stop because the general chair is calling us for closing the session. I think it was, in any case, a great opportunity. I don't know, Ernesto, if you will allow to share these slides with the participants.
Yeah, please. The slides are available, and also any comments or question or collaboration, interest, whatever. Well, I'm here. I would be very glad to be able to exchange ideas with the participants to this workshop. I think this is a very important and timely workshop. So again, congratulations for running it. I think that it is a very important topic. And there are so many angles that we couldn't explore in this particular presentation that still are very, very interesting.
Yeah, we are just at the starting of our journey. So let's see you on the next section, that is 13:30, and see you later. Thanks.
Thanks, everybody.
Bye-bye.